Hey guys, welcome back. So we are going to be talking about the Vesper lab today. That's Virtual Lab 10, and I think this is one of the more fun virtual labs to do. I think there's a lot of good information that you can gather from doing this lab. So I'm going to go ahead and share my screen. I will do the same thing, and this virtual lab. Is based on Lewis dot structures and then molecular geometry. So it's chapters 9 and I think it's 9 and 10 that are involved with this. Okay, so you won't be able to do this until you've done the molecular geometry as well. Now I'm gonna reset. There's a reason to do that. So, oops. Okay. So I'm going to do two of these. There's more than two here, but there are two of them that I want to be able to walk through with you guys. So the first one that I want to talk about is CH2Cl2. As I mentioned in the lecture, when we do this, we say CH2, Cl2. The thing that's written first goes in the center. But we need to know how many valence electrons each one of these things brings to this party, right? So I'm going to be looking at my periodic table to be able to do that. And I actually closed it. Oops. Sorry about that. Should have been prepared. So, that is not my twos. Sorry. If it ever actually loads. Oh, there we go. Okay. So I need to be able to look at this periodic table to be able to do this. I'm going to try and. Nope, I can't. So if we look right here, so this one right here, that's carbon. Now, carbon is in the second row, and he's in the second column over in that block on the right-hand side. So I would expect his electron configuration to be 1s2, 2s2, 2p2. Now my number of valence electrons is the number that are in that outermost shell, so in the 2. So I have 2 s electrons and 2 p electrons for a total of 4 in that outermost shell. So he has 4 valence electrons. There's one of him. And so that brings me 4 electrons to this party from carbon. Hydrogen is right here. Now, since he's number 1, I would expect him to be a 1s1. So each one of them has 1 electron. There are 2 of them, total of 2 electrons brought to this party. And when we talk about chlorine, chlorine is over here. He's just before argon. So he's in the third row. So I would expect him to be a 1s2, 2s2, 2p6, 3s2, 3p5. 1, 2, 3, 4, 5. So 3p5. So 5 p's, 2 in the s, it's a total of 7. And there are 2 of them, that gives me 14. That's my total of 20 that I have for this particular grouping that we want to look at. Okay. 2 right. There it is. Okay, so that's where this 20 comes from. Now, when I draw my Lewis dot structure for this, I have carbon in the middle, because that's the first thing that was written. I'm going to have a hydrogen, chlorine, and a chlorine. Does it matter where I draw them? No, it does not. I know that I need one bond between all of them, and that each of those bonds contains 2 electrons. So I have 2, 4, 6, 8 electrons that are taken up in those bonds. If I take that out, that leaves me with 12 electrons that I still need to distribute. And the way we do this is to fill the octets for everybody on the outside first. But hydrogen doesn't need an octet, it needs a duet, so 2. There are 2 electrons in this bond, and both of those are accessible by sharing to that hydrogen, so he's happy. Hydrogen is good. Chlorine, on the other hand, is not. Okay. So we're going to take, and since we only have 2 electrons that are available to each chlorine, we need to add 6 additional electrons to each one to give it an octet. That makes 12, so there are none left. That's good because none need to go on carbon. Remember that carbon brought 4 to this party, so if we look at a formal charge for carbon, that would be the 4 that he brought, plus the 1, 2, 3, 4, half of each of those bonds, 4 that he has access to, so his formal charge is 0. If we wanted to do the formal charge for hydrogen, 1 out of each of those bonds, that's a 0. And if we look at the formal charge for chlorine, 7 electrons were brought by each chlorine, and each chlorine has 2, 4, 6, and 1 from that bond, 7 that they have access to, so that's 0. Okay, since my formal charge is minimized, I have all of my electrons distributed. That is the structure that I will be looking at. Okay, so that's what I'm going to do. Now, the reason that it's not like this is because we don't have that hydrogen bound to chlorine. Okay, it's bound to the carbon. So this is not going to be a reasonable structure. This one, it's not chlorine then hydrogen. That's not how it's bound. Here, this is close, but that's a chlorine in the middle, and that's not right. So this is the one that I chose, which has the carbon in the middle, 2 chlorines on the outside, and 2 hydrogens on the outside. Okay, awesome. Now, I'm going to come here and I'm going to reset this because I want to walk you through how we do this part. So, since I don't need to show my drawings for the moment, select the central atom. Now, if I can't remember which one they are, I can use this show labels. And it says carbon, oxygen, nitrogen, chlorine, hydrogen, multiple bonds, single bonds, and here's my stand. So since carbon is my central, I'll click count. Select each terminal atom to place on the lab bench. So I need 2 hydrogens and 2, no, wrong one, 2 chlorines. Okay. Now, I know that I need to have each of my single bonds placed on the lab bench. So there were 4 bonds, right? 1, 2, 3, 4. I put my carbon on the stand, and then I put each of these bonds into the holes that exist on this particular shape. So if you look in here, you can see that there are holes that exist where those bonds can go. So that determines the base structure that we're looking at. Okay. Now we want to add our terminal atoms to each of these. And I'm going to put my hydrogen and my hydrogen, chlorine and chlorine. Now, why did I put them in that order? It doesn't matter. And I'll show you that again in just a minute. I know I've said that before, but it doesn't matter. I'll show you in just a minute why. Now I need to come into my lab data, and they want to know, for this particular structure, how many bonding groups are around that central atom. I have 1, 2, 3, 4 bonding groups, and no non-bonding pairs. So I have 4 there. I have a 0 there. And now once we come out of here, and it says click completed structure to rotate. So I click it and it takes me in, and what I can do is take this structure and turn it all kinds of different ways. And what you can see is that no matter how I turn this, those 2 hydrogens are next to each other, those 2 chlorines are next to each other. So it doesn't matter how you turn it, and that's why it doesn't matter where you put them. Okay, so that's why. It's because of the 3-dimensional shape of this particular structure. So you can play with that. You can zoom in, you can zoom out, you can do all kinds of stuff. So there's that. And that's one of the things, excuse me, that I really like about this is being able to see that it's equivalent because of that 3-dimensional structure. Okay. So I'll close that out. And the next thing it says is determine the electron pair geometry and the molecular geometry. So I need to open this up. And down here at the bottom, there's a geometry table. So if I open this geometry table, it says 4 number of groups around central atom is 4. Okay, so that's tetrahedral. That's my electron pair geometry. And then the number of lone pairs on the central atom is 0. So that's also tetrahedral. Now, in my mind, that makes complete sense because it's only going to be a different structure between the base structure and the exterior, or the electron pair and the molecular pair, if one of those is non-bonding. Okay, so since this is not, it's going to be tetrahedral and tetrahedral. Okay, now I'm going to go past 3, past 4, because I want to talk about this guy right here. So this is HCN. Now, why do I want to talk about HCN? Because HCN breaks one of the rules that we've talked about. So HCN is written like this. And so based on what I've told you, I would think that that hydrogen would go in the center, but it can't. And that's because it only gets a duet. So he can't go in the middle. Okay? Hydrogen is never a central atom. So the next thing that's written is the central atom. So that's the carbon. So we're going to have a carbon that goes in the middle. We're going to have a nitrogen on this end and a hydrogen on this end. But I need to know how many valence electrons I have for this structure. A hydrogen, a carbon, and a nitrogen. We did the hydrogen before. It had 1 valence electron. There's 1 of them, so that's 1. Carbon had 4 valence electrons. And there's 1 of those, so that's 4. And nitrogen, well, where is nitrogen? Let's go find it. Well, nitrogen is actually right next to carbon. So if carbon had 4, nitrogen then has 5. So 3 in the P, 2 in the S. So 5 total. So 5 there, 1, it gives me 5. Total then is 10. Okay. So that's where I get this 10. Now I know that my carbon's in the middle. I need to draw at least 1 bond between the hydrogen and the carbon, and between the carbon and the nitrogen. Now that takes up 4 electrons. 4. So there's 6 that I need to accommodate somewhere in this structure. And we always fill the outermost guys first. So we're trying to fill our octets. But hydrogen doesn't want an octet. It wants a duet. It can only have those 2. And so you can see in this bond, it already has 2. So all of those 6 electrons are going to go on this nitrogen. 1, 2, 3, 4, 5, 6. Okay. And that leaves me with none left to distribute. Okay, awesome, right? Sort of, kind of. And there's 2 things that stand out to me here. 1, carbon does not have a complete octet around it. Okay, the other thing that stands out to me is if I look at the formal charge. So if I look at the formal charge, carbon, or hydrogen, carbon, and then nitrogen, when we do formal charge, hydrogen brought 1 electron to this party, and he has access to half of what's in this bond, so 1 electron there. So his formal charge is 0. Cool, awesome, he's totally happy. When we look at the formal charge on carbon, he brought 4 to this party, and he has access to half of each of these bonds, so 2. That gives him a +2 charge. And nitrogen brought 5 to this party, and he currently has 2, 4, 6, 7 that are associated with him, and that's a -2 charge. Now, is the net charge on the entire molecule what it should be? Yeah, it is. But we have formal charge on carbon and nitrogen. So we want to try and move those electrons somewhere so that we don't have formal charge. Okay. The way that we do that is by taking one of those lone pairs off of nitrogen and moving it to create a multiple bond. So we're going to take one of these pairs and make a double bond. So I'm going to take that one pair and move it right there, and now I have a double bond. That changes the number of electrons that are available to each of these, so I'm going to delete those. Okay, carbon still wants those 4. He now has 1, 2, 3. Nitrogen wants 5, has 1, 2, 3, 4, 5, 6. So this is a +1, this is a -1. We're still not happy. So because we're still not happy and we still have lone pairs that we can move, we're going to move another lone pair. So I'm going to take this lone pair away, and I'm going to draw another bond. Now, that's a triple bond because we have 2, 4, 6, 2, 4, 6 electrons that are in there. So that's a triple bond. Now, when I do that, it changes the electron distribution. I now look at carbon. He has 1, 2, 3, 4. So half of each of those bonds belongs to him. So that's 4. That gives him a 0 charge. Nitrogen has half of these electrons. So 1, 2, 3, 4, 5. And that's also 0. So that's the structure that I'm going to want to choose. Okay, that is the one that I've chosen here, and that gives us the structure that we need to look at. Okay, awesome, possum. Now, I'm going to reset this one so that we can see how do we build this thing. Sorry. Actually, don't need this anymore, so I'm going to minimize this. I apologize for that. Technology doesn't always love me. So central atom is that carbon. So I'm going to put him down. I have 1 hydrogen and 1 nitrogen. So that's everybody. It says to put a single bond, and that's for the one between the hydrogen and the carbon. And then we have 1, 2, 3 bonds between the carbon and the nitrogen. Now I put my central atom on the stand. It says attach 1 multiple bond to the central atom. Okay, awesome, I put it there. Attach terminal atom to the multiple bond. So I pick up the nitrogen and I put him here. It says attach remaining multiple bonds. So I take this one over here and I take this one over here. So now I've got all of my multiple bonds between those two. Now I take this single bond, put him over here, and put his terminal atom. So the number of bonding groups around the central atom is actually only 2. And the reason that it's only 2 is because multiple bonds have to exist in the same physical space. So they can't be in separate positions around this guy. And because of that, we only have 2 bonding pairs that we need to worry about. When I pull up my lab data for this, I have 2, and there are no lone pairs around that central guy. So that's what we're talking about there. Now I come out here and I click this, and I get to look at everything. Oh, this is awesome. And what I want you to notice is that even though there are multiple bonds, they are in the same physical space. If I were to take this bond right here, one of these multiple bonds, and move it to a different part of the carbon, which would then indicate an additional bonding pair, it wouldn't be bound to the nitrogen. Okay, that's why we consider multiple bonds to be one bonding pair. Okay, so that's how that works. You can play with this all you like. Now, the next thing I need to do is to determine the electron pair geometry and the molecular geometry. So if I go into my lab data, come down here to my geometry table, I have 2 pairs around the central atom, no lone pairs. So that is linear, and my molecular geometry is also linear. Okay. So when I choose this is linear, and this is linear. And then I'm good. Okay. Now, that takes me to the next one, which I'm going to let you guys deal with. So you can do the rest of these on your own. That should take you through any of the questions that you would run into with this. Okay. So remember, a couple of things. How many electrons, valence electrons, are brought by each of these people to this party? So we have a total count. We draw at least 1 bond between everybody and subtract those electrons out. We then fulfill the octet for everybody on the outside. Okay? When we've done that, we subtract those electrons out, and any that are left would go on my central atom. Okay? We then look at our formal charge. If our formal charge is 0 everywhere, then we're done. We're good. We're happy. If it's not, we start trying to move those electron pairs, those lone pairs, into multiple bonds to minimize that formal charge. Okay? So those are your steps. When you do this, it should always be those steps in that order. So try and remember that. And I hope that helps. And I hope you have fun doing this lab. Thanks, guys.